My name is Michael Heeschen, and I was working with Dr. Harry Kay throughout the summer developing the level structure and spin assignments in gallium-70. Now, the purpose for this research was to add to the experimental knowledge that helps develop the theory in the Wild West region of the nuclear landscape. Now, if you look on your image to your right over here, the Wild West region is down here, and this is a purely theoretical graph. So the purpose of this research is to help develop this region of the graph. And as we can see, the deformation versus non-deformation changes very rapidly in this region. Warmer colors represent highly deformed nuclei, while cooler colors represent not deformed nuclei. So to help with that, we're looking for signs of deformation within this nucleus and also looking for signs of rotation within gallium-70. And on the level scheme, we're looking for this type of structure, this band-like structure with a spin change of 2 with regular gamma ray energy increases above the spin 9 state. Now don't worry what that means yet, I'll get to explaining it in a second, but just keep in mind that this is the type of structure that we're looking for. And this is actually an image of gallium-66, which is a very closely neighboring odd-to-odd nuclei. So we expect to see a similar type of structure in gallium-70. Now, how we acquired data for this experiment is we launched a beam of carbon-14 at a nickel-62 nucleus to create selenium-76. Now, the selenium-76 has a ton of energy and wants to get rid of that energy as quick as it possibly can. And the easiest way for this to do it is to release small particles in the form of alpha particles, neutrons, and protons. To generate gallium-70, it needs to release one alpha particle, one neutron, and one proton. But that's not the only combination of small particles that can be released. So a lot of different nuclei can be generated during this experiment, and they were. But with the gallium-70, after releasing one alpha particle, one neutron, and one proton, we get an excited gallium-70 nucleus, and it wants to release its energy as quick as it can as well. But it does it not by releasing small particles, but by releasing things called gamma rays, which are just very high-frequency light outside the visible spectrum. So as it releases these gamma rays, it tries to get down to its happiest state or its ground state. Now, this is what the data looked like for the experiment, just the raw data without any filtering going on. So this shows all the gamma rays for every nucleus that was generated during this experiment. Luckily, we don't really have to look through this because finding gallium-70 in here would be impossible because gallium-70 was only created about 1 to 5% of the time. So the most prominent gamma rays, the most strong gamma rays in gallium-70 are likely lost in the background here. Well, we can rectify that using filtering techniques that I'll get into in a little bit. But before I get into that, I want to kind of show you guys where we're starting off. So this is the previous study's level scheme for gallium-70 at high energy levels. And this was published back in 1976. So it's been about 40 years since gallium-70 has been studied at these high energies. As you can see, there's really not a whole lot to this map. But if you look at what we've generated, as you can see, we've added a ton. This was not all done by me, but it was done by me, Dr. HK, and our colleagues to develop this level scheme. But everything in red has been added new, and the things in black have been confirmed from that past level scheme. Now, there's a lot of information embedded in this level scheme, so we're going to kind of break it down piece by piece. And we're going to start off with these horizontal lines here. These are called energy states, and quantum mechanics dictates that gallium-70, through its decay, can only occupy discrete energy levels. So it can't go to any energy at once. This is the map of gallium-70 as far as we know, as far as we've produced. Now, the arrows that are linking these energy states are actually the gamma rays that we measured. And the number in the middle is the kiloelectron volts of that gamma ray, or the energy of that gamma ray. And the thickness of the arrow represents the intensity of that gamma ray, or how prominent it was in our data. Now that leads to the question, how are we able to measure these if that raw data was just so hectic? Well, we used a filtering technique called gating. And basically what gating means is you choose one of these gamma rays to gate on, for example this 1230, and you will only see gamma rays in series with that gate to ground. So for example, if we're looking at this 554 and we gated on the 1230, there's a clear path to decay through the 554 and down through 1230 to ground, but we don't expect to see the 771 because the decay path cannot go through 1230 and also through 771. So after we gate, this is what our level scheme would look like if we were to gate on 1230. So as you can see, a lot of gamma rays were removed, and that helps us see weaker gamma rays in the data. And also what gating does is, as you can see, we didn't see the 771, so if we gate on a bunch of different gamma rays, it kind of creates puzzle pieces so we can start to fit this level scheme together and place gamma rays in the correct position. So that's how we got all these things situated where they are. Now to give you an idea what the data looks like after gating, it looks a lot cleaner. Most of the gamma rays we see here belong to gallium-70, and if, as you can see, the background went way down, if you compare it back to the raw data from before, all these gamma rays would likely be lost in the background here. So gating is a very powerful technique in order to analyze this data. Now the next thing we're going to look at on this level scheme are these numbers on the left side of the energy states. These are called spins. And basically what spin is just a quantum number for angular momentum for that energy state. Now, in this region of the nuclear landscape, in this mass region of the nuclear landscape, there are two transitions, gamma ray transitions that are the most prominent. They are dipole transition and quadrupole transitions. And what they simply mean, a dipole transition means a spin change of 1. So we look back at this 1230, the spin goes from 8 to 7, so we know that 1230 is a dipole transition. A quadrupole transition is a spin change of 2. So if we look at this 188, we see that the spin goes from 4 to 2, so we know that spin change is 2, and it is a quadrupole. So that brings up the question, well, how did you measure things like 12 and 13? Well, we used a technique called directional correlation of oriented nuclei ratio, or DCO ratio for short. And this comes from an extremely complex angular theory that basically says, depending on the angle our detector is from the beam, the carbon-14 beam, we will see different intensities for gamma rays given off by the gallium-70 nucleus that was created. So how we calculate this is the gamma ray intensity at 35 and 145 degree detectors gated by the gamma ray on the 90 degree detector divided by the intensity at the 90 degree detector gated on by the 35 and 145 degree detector. Now that sounds really complicated. It is quite confusing to wrap your head around, but basically what it is you divide the area under the curve, or the intensity of the 35 and 145 degree spectrum by the area under the curve, or the intensity of the 90 degree spectrum. So if we look at this 188 gamma ray here, we can see that this intensity is about 12,000, while in the 90 degree detector it's about 6,000, so that DCO ratio is about 2, which represents a quadrupole. And if you guys remember before, we saw that 188 is a quadrupole transition. If we look at this 200 kilo electron volt gamma ray, we can see that they both have about 5,500 counts, so that DCO ratio would be about 1, which represents a dipole. And then after we did that calculation for pretty much every single gamma ray here, it just turns into a counting game. So we know the 691 is a dipole transition, so the ground state is 1, so we know that this needs to increase by 1 to 2. We know this 188 is a quadrupole transition, so it goes from 2 to 4, and all the way up the level scheme, until we have a spin assignment for every state. Now, our results of the experiment were pretty much exactly what we wanted to see. We saw that band-like structure that we wanted to see at the beginning, this one here, so that's evidence of rotation and deformation within the nucleus. And those spin assignments also let us graph a static moment of inertia versus spin graph. And if we look down here, this is a lot of graphs for static moment of inertia versus spin for many different odd nuclei that are known to rotate and are known to be deformed. So as we can see here, our graph for it resembles the shape that we've seen in past, so we can pretty confidently say that our nucleus, gallium-70, both rotates and is deformed. What else these spin measurements brought out was a graph of energy differences versus spin of the parent state. And if we look on the right, again, at high spin, we expect to see this normally increasing zigzag pattern. But in our nucleus, we start to see this zigzag pattern, but for some reason at this high spin, we see a phase shift. And we're not sure why we see this phase shift. And whenever you see something that you don't expect and you don't understand, it's reason to investigate it further. Well, unfortunately, this graph was produced at the end of the summer, so I didn't have time to look into this. But I know Dr. Herring Kay is looking at studying this further throughout the school year and next summer with his next students. Thank you. Are there any questions? Yes.
To go back to the static moment of inertia slide, do you happen to know why, like, nuclei in this region form that pattern?
I do not know why they form this pattern. Just through experimental study, it has been reoccurring that this pattern appears in rotational and deformed nuclei.
I think the general thought is that the high moment of inertia, low spin and low angular frequency, is individual particles dancing around. So there's a little more, crazy behavior going on there, and then they settle down to, they converge to what's called the rigid body value. So now you have basically a rotating rigid body, so much more regularity in moment of inertia.
Yes.
What makes it an odd nuclei?
An odd nuclei comes from this right here. So basically, in these energy levels, it is occupied by two neutrons and two protons, and at the highest energy level, one neutron, one proton are unpaired. So they are free to hop around between different energy levels without a whole lot of resistance because they're not tied down to another pair. So at low energy levels, if we look back at the level structure here, at low energy levels, it's not as organized, it's quite a bit more hectic, and that's why at high energy levels, we expect to see this band, which is a lot more structured, because then the angular momentum is dominated by rotation as opposed to being dominated by those two, those free proton and free neutron that are bouncing around.
So gallium-70 has 31 protons and 39 neutrons, both odd numbers. That's odd. And what Mike said.
In a simpler state.
You have questions for Mike?
Yes.
So I'm sure you probably explained this, so, and if you did, you can ignore my question. But what I'm understanding here is that the numbers on the arrows are something like the wavelength of the gamma ray that's emitted during that energy transition?
No, the number on the arrows is the energy of that gamma ray.
Is the energy of
Yes.
the gamma ray?
So the energy of this gamma ray, energy along the x-axis, is 155 kiloelectron volts. And we see that 155 right here.
How do you distinguish? So you have two arrows that are 915. How do you distinguish
Yes.
between those two transitions?
This caused quite a bit of trouble through our research. For some reason, we were seeing 915 as having too high of an intensity. So energy must be conserved. That is one of the fundamental laws of physics. And as you can see, as we go down the level scheme, the arrows tend to get thicker and thicker as they go down a preferred path to decay, which is quite, the easiest one is just a straight down one. And so we can't have a super thick intensity 691 going into something like a 554. The thickness of the arrows kind of have to match up. So basically, it's like 1 plus 1 has to equal 2. 2 plus 1 can't equal 1 type of thing. So we saw this 915 kiloelectron volt gamma ray having too high of an intensity. So what I noticed was that the difference between, this was originally, this one right here was originally the one that was here. And what I noticed was that this energy difference was also 915. And So I had thought that there were I originally thought that this 914 down here was bleeding over into the 915, but that proved to be not true. So we think that there are two back-to-back 915 gamma rays, and that's pretty rare, but it fits the puzzle perfectly. This was one of the last things I put into the level scheme, and it really didn't come about from until I had measured the spins, because as I started measuring the spins, this band-like structure up here started to become more and more apparent, and for this band-like structure to really make sense, we needed another thing here. And then I remembered back to whenever I noticed that this 915 had too high of an intensity. So that those two pieces of evidence really solidified that there is more than likely two 915 gamma rays stacked on top of each other.
Just to quickly summarize, the intensity flux into a state must not be greater than that coming out. And a single 915 keV transition would have violated that.
Yes?
And I presume that the fact that, what is it, I guess, 554 plus 361 equals 915 played a role in that determination. Like it looks like it's just two paths to get to that same 10. I think it's a minus state.
10 plus, it's a little difficult to see. But yeah, it can follow either path, but chances are it'll go down through the 554 path because it wants to get to this band here.
That's conservation of energy in action. Any other questions for Mike? All right, let's thank him again.